Okay, now that we've talked relativistic energy and momentum, we have to go one step further and talk about actual relativistic dynamics. Okay, and here there's a first statement to make, which is quite simply that Newton's second law is okay. Newton's second law, it's okay, it still holds. Provided we use the relativistic momentum. Yeah, but for the relativistic momentum, that is, if I look at the force on a certain object, I will associate it to the time rate of change of the spatial part of the relativistic momentum. Okay, and here there's actually a really nice example in Griffith's book, which is motion under a constant force. Okay, it's example 12.10. So what's the idea here? A particle has particle of mass m at x is equal to 0, at t is equal to 0. And it's subjected to a constant force F. In the x hat direction. Okay, so what does that mean? The question is, you want to find the position of the particle as a function of time, okay, in the ground frame. So how do you go about doing that? Well, it's quite straightforward. You look at the equation. So Newton's law here tells us that the dp dt is just the force and is a constant, and p of t is equal to 0 is equal to 0. So that means that p is just equal to f times t. So if you want, just looking at this. At our equations for the relativistic momentum, so p of t is going to be mu of t over the square root of 1 minus u squared of t over c squared. Okay, and this has to be equal to f times t. And from this, we can just isolate u of t. So u of t is equal to f over m times t. All of this divided by 1 plus f times t over mc squared, and all in a square root. Okay, so it's just isolating the u of t from that equation. Right, now to get x of t, just integrate this thing. So x of t is going to be f over m with the integral from 0 to t over auxiliary time t prime of then just this formula here evaluated at t prime. So I've got t prime divided by the square root of 1 plus f t prime over mc all of this squared, and then the square root. Okay, and so this this integral, you see, is quite easy because I already have the t prime here. When I take a t prime derivative of this, I just get the the t squared gives me a 2t prime dt prime, which is exactly what I have here. So this can just be directly integrated. The factor of 2 that I get from here cancels from the square root. So the integral is just proportional to the square root of this object here. And then I need to correct for these factors here that are squared, right? So I have an m squared c squared divided by f squared, but then I do f over m. So that just leaves me with an mc squared divided by f. And then I have the square root of this evaluated between 0 and t. So I get a square root of 1 plus ft over mc squared square root. And then minus the same thing evaluated at t is equal to 0, which is 1. Okay, so that's the solution for the position as a function of time. And this is quite cool, right? Because you plot this as a function of space and time, and that's this this like hyperbolic-like motion that you get. Okay, so so essentially it asymptotes to something moving at the speed of light, but along this this hyperbola curve that you have there. Okay, so now that we've discussed this nice example with motion under constant force, we can move on to talk about work and energy. So here it's also quite straightforward because the work done in the relativistic case is still the line integral of the force. And as we've seen before, the force is just the time differential of the relativistic momentum. Okay, so we want to calculate such an integral here. Now, what we can do is just parameterize the displacement with time. So essentially, I'll want to do a time integral of dl dt dotted into dp dt. Now, we've identified the dl dt with u, okay? So you remember the ordinary velocity here. Now, let's just look at the combination that we have here. So if I am to look at dp dt dotted into u, then what do I have? Well, this is, by just substituting for the relativistic momentum, this is just d dt of the following thing. So I have mu divided by the square root of 1 minus u squared over c squared. Okay, and that has to be dotted into u. So let's try to do this step by step. If I, well, maybe I'll just do it term by term. So there are two different terms that come here. First of all, I can just factorize the m out completely. And now what do I get? I get 1 over the square root of 1 minus u squared over c squared with the du dt. Right? That's just acting with the differential on this one. And now I want to act with the differential on this one. So what do I get? Well, I get something which is 1 over the square root, so exponent minus 1/2. So I will want to have let's just do it straight. So I've got the u here, and then this is going to be multiplying the following things: the ddt of 1 over the square root, so minus 1/2. Okay, then the derivative of this, but the derivative of this, you see, is going to be 1 over c squared with now a minus 2. With u dotted into du dt. And this whole thing is going to divide 1 minus u squared over c squared to the power 3/2. Okay, and then this whole thing here is going to be dotted into u. Okay, so we can try to rearrange terms a little bit. So first of all, the plus, the minus signs cancel, the factor of 2 cancels here. And then you see I can factor out a u dot du dt. So I've got an m, a u dotted into du dt. And now the parentheses, right, 1 over square root of 1 minus u squared over c squared. And then plus what have I got here left? I've just got u squared over c squared divided by 1 minus u squared over c squared to the 3/2. Okay, so you see what I can do is just put all the same denominator everywhere. So I would have a 1 minus u squared over c squared here with this over the 3/2, but then the u squared over c squared cancels. So this whole thing becomes quite simply mu dotted into du dt divided by 1 minus u squared over c squared to the 3/2. Okay, so that's one expression. Now, the point is that if you look at it at this level, you can immediately recognize that this is just the time derivative of the quantity just m, and I'll put back a c squared because I want to take a derivative here, divided by the square root 1 minus u squared over c squared. Right? And this is just the time derivative of the energy that we've defined, the relativistic energy. Okay? So that's just a relatively straightforward derivation to show that indeed the work is related to the time rate of change of the energy, right? So the total work done. Well, actually, that was just the integrand, right? So I mean the integrand here, not the work, just the integrand of the work is the time rate of change of the energy. So then, when I reintegrate for the whole work, I just end up with dt d dt, which is just integral of dE, which gives me the change in relativistic energy. Okay, so that's the way you associate these things. Now we can talk a little bit more about the force. The problem with the force is that it does not transform well under the Lorentz transformation. Okay, so for example, let's say we go to again a frame moving with velocity v as compared to a first one, and we want to compute the new value of the force. Let's say we take an example of motion along x that we had. So the transverse components of the force, what would this be? This would be d py in the new coordinate system with respect to t bar, it's b. And then we can just use the transformations that we had. So the t bar is just related to the previous one by the law that we saw, beta over c dx. Okay, so this was just the Lorentz transformation law that we had, and this I can just rewrite as dpy dt divided by gamma. So I just divided by dt everywhere. 1 minus beta over c dx dt. Okay, and this, if you just like re-identify, this is just the force in the original frame, divided by gamma of 1 minus beta the ux over c. Okay, and the same occurs for so similar for the z component of the force. For the longitudinal component of the force, we have to do a little bit more work. So fx is going to be dp bar x dt bar. And now I need to do the more complicated transformation on the numerator. So I've got a gamma dpx minus gamma beta dp0 divided by gamma dt minus gamma beta over c dx. Okay, so all the gammas fall off, and as above, I just divide by dt everywhere, so dpx dt just becomes fx. And now I've got beta over c de dt, just by the definition of the x0. And in the denominator, I get similarly to this, just without the gamma, 1 minus beta ux over c. So what is this? Well, actually, this d dt, you remember, we just calculated it, right? It was just u dot f. Yeah? That's what we just did here. We just showed that u dot f was equal to de dt. So I can, again, use this, this form in here. And kind of cleanest way of writing this is as follows: beta, and now u dot f, okay, all over c, divided by 1 minus beta ux over c. Okay, so that's the transformation law for the force. You see, it's not very nice. So you can take a specific case that'll be useful later. Case when the particle is instantaneously at rest. In the original frame. Then in that case, you can see it simplifies because there's just a 1 over gamma for the transverse parts, and the longitudinal part just becomes the original one, right? So the y and z components would just pick up a 1 over gamma, whereas the longitudinal part would just pick up a factor of 1. So in that case, we could just write that the force transformed perpendicular to the force in the original frame is just 1 over gamma times the perpendicular force in the original frame. Okay, and these are now like vector quantities, and the transformed parallel one is just the previous one like this. Okay, so that's a very simple case. Doesn't work everywhere, but at least for that particular case it works. Okay, so we might want to avoid complicated transformation rules. And you'll guess what we'll want to do. We'll want to use proper time instead of normal time. So to avoid complicated transformation rules, we can define an object that's called the Minkowski force. Okay, and this Minkowski force, symbol K, not a surface current, just K, is the rate of change of the relativistic momentum with respect to proper time. Okay, and this you can just like rewrite if you want as dt d tau times dp dt. Okay, and these two independently we've calculated it because that's just the gamma factor, 1 minus u squared over c squared times the force. Okay, so that's a quantity that transforms more beautifully than the original force. And we can also consider a zeroth component to this to make it a proper 4-vector. So this zeroth component, k0, would just be, again, by the same definition, dp0 d tau. And this, by the identities that we've seen, is just 1 over c dE d tau. Yeah, because you know that P0 is just related to the energy with 1 over c factor. Okay, so that's just the kinds of basics of relativity that we needed to go through before we can really start talking again about electrodynamics, which we'll do in the next little lesson.